My project was playing trivia games by playing the Wikipedia game. Explain those if you don't know what those are. Quick overview. So getting right to it. So my area of research is in question answering, and we're trying to do that by learning how to play trivia games so that we can learn how to do general question answering. So if you have your phone and you ask, I'm not going to say the keyword, but you ask your phone a question, who's the president of the United States? That would be an example of question answering. We're playing a game called Quiz Bowl to do this, which is not quite the same question. So this is played by middle school students, high school students, college students all around the country, all around the world. And it includes questions in history, literature, science, basically all kinds of academic trivia questions. So if we were to play now, let's say if I played against Aaron, someone would read a question, and then when one of us knows the answer, we'll buzz in and say, well, the answer is whatever. So rather than trying to explain that, let's do an example. So if you've seen this question before, please don't answer. But with Leo, he invented a doubly eponymous refrigerator with no moving parts. He did not take into account interactions with neighbors when formulating his theory of heat capacity. So WA adjusted the theory for low temperatures. His summation convention automatically sums repeated indices and tensor products. His name is attached to the A and B coefficients. For spontaneous and stimulated emission, the subject of his multiple groundbreaking 1905 papers, he further developed his model statistics sent to him by... Yeah, when you know the answer.
Einstein.
Yeah, so the answer is Einstein. So an interesting thing here is that the answer is very difficult to know at the beginning, and then it becomes easier at the end. So this is the essential task, is we get a bunch of questions like these, and we're trying to answer as soon as possible. For this project, I just said, well, let's try and answer at the end of the question and see how well we can do. So the high-level overview of our current system is we get some question text, and we have to somehow form a text representation, either with word2vec or n-grams, and encode it as a feature vector. Then we have some model, F, that turns that into a list of whatever top guesses we think is possibly the answer for this particular question. And then there's some downstream stuff that decides when we should buzz and when we should wait. But the question for this project is, right now, our F is a deep learning-based model. Can we create an F that is a network-based F? So the reason and motivation for this is that currently we're using deep learning and essentially what amounts to a multi-class classification model. However, the number of answers or classes that it could be is extremely large. In our data set alone, there's about 12,000 unique answers, which makes it a very difficult multi-class classification problem. And you also need many examples per class. But some questions are asked much less frequently than others. So the worst case scenario is questions that are asked only once. And to show that this is a problem for our data set, if you take our data set and filter by classes or answers that have at least 5 training examples, which is what we currently do, then the answers drop from 12,000 to 2,000 that we could possibly answer, and we can only answer a little more than half the questions in our data set, which is not great. So a goal for this project is let's try and get at this problem by not limiting ourselves in the answer classes too much. So these are the goals. We also want our network model to be fast. So for this, I used a Wikipedia-based approach, and this is just getting the point. The Wikipedia graph is sort of large, and this was as of 2010. So now I'll explain the inspiration for the approach. So the inspiration comes from the Wikipedia game. So if you haven't played this game, you start at some page, say Bond Girl, and you use the minimum number of clicks to get to the history of Wikipedia. So for example, in our question, how many hops away is Einstein from Leo? Well, he's mentioned right in the right part of the page, so it's right there. If you look at refrigerator, though, it's 2 hops away. You have to first go to absorption refrigerator and then to refrigerator. And these are related, but the point is that something in a question is some number of hops away from the answer. So we can treat Wikipedia as a directed graph. So nodes are Wikipedia pages, and edges are hyperlinks from one page to another one. And the game is to find the shortest path length from a given vertex to the end vertex. So the hypothesis that we had was that if we play the Wikipedia game, starting at the answer that we're considering, and then go to each entity mentioned in the question text, then the mean number of hops is less than starting from any other entity. That is to say that the answer should be closer to the things mentioned in the question than anything else, which makes sense, and we would hope is the case. So this is the network version that if you take the embedding of a text question in, say, ngram or word2vec and project it in some space, that answers that talk about the same answer should occupy similar places in that space. So this is trying to get a network way to do that. So the goal is to devise a method that takes advantage of this hypothesis being true. So we would first create a set of candidates that we think are possibly the answer. And then for each candidate, we're going to score it, and we're going to score it by computing the Wikipedia game distance from each entity to the answer. Sorry, the answer to each entity in the question. And then we're going to return that list of candidates sorted by the lowest distance. So the obvious question is, how do we get a list of candidates? Well, all the answers would be much too slow. However, as it turns out, if we're talking about things related to Einstein or things related to, say, physics or Leo, we probably only need to go a small number of hops away in the network in order to capture the answer. So for the experiments that I do, I just take all of the things mentioned in the question and go one hop away. So for example, in the blue are things mentioned in the Einstein question, and I do some crude matching just to say, well, if it's an exact match with a Wikipedia page title, then there's a match. So far I've done unigrams, but I'd like to try bigrams. So for example, this is the page for Leo. All the blue links are hyperlinks. So those would be all the things I would include as potential guesses. So preliminary results, I've tried questions that have only one training example, so things that our current system could never, ever get correct. Took a 200 question sample. Of those, 70 questions using the method before somehow in the list of candidates include the answer. So that is 70 of them are answerable. And in the results that follow, a higher score is better because I'm scoring by the inverse distance so that the math works out. Also the point being, it's more important that the answer is captured in the top 200 guesses than that the top guess is correct, because later we do other features like the language model, et cetera, that can do well if the answer is in the top 200 or so. So here, 4 minutes. So here, I'm going to present some results, and this is kind of the format. So I'll have the answer, whatever the answer is, then the answer distance. So this is the sum of the inverse distances for going from, say, Leo to Einstein, or some other answer to Einstein, or refrigerator to Einstein, et cetera. So those distances. And this is for the candidate guess that is actually the answer, what was the distance? And then we need something to compare against, so we take the mean distance score, and then for useful statistical purposes, we take the standard deviation. And then num candidates is with the capturing process of taking all the neighbors, how many candidate guesses did we have? And then num to answers is how far down the list do we have to go in order to find the actual answer? So that's hard to read, so I'll just talk about this slide. So what I'm looking for is that the answer distance is above the mean distance by a non-trivial number of standard deviations, and that the num to answer is hopefully 1 or just low. So I ran this on the 70 questions or so, and since it's kind of hard to see, I'll point out these green are, this was in the top 1, top 7, and the red are very bad, like 15,000 out of 3,000, or 1,500 out of 3,000, and 900 out of 4,000. But the promising thing here is that we're getting some correct. And when I looked at the data, the interesting thing is that, for example, this one is a question about the Aztecs, is that the question text had, for example, a bigram that I had not been including because I'm doing unigram matching for the Wikipedia page titles. So if I include that, then it's very possible I get this one much better than I did before. So that is to say that already with a extremely crude method, it's doing something that appears useful. So looking at samples is useful, but it's also useful to have aggregate performance metric. So this is essentially a recall plot. So this is, of the 70 questions that I could have answered correctly, how many guesses am I taking in order to get the right answer? So it's good that this kind of goes up rather steeply. And the point that I care about right now is that at this 200 guesses, what's the recall there? And it's around 60% recall. So this is extremely encouraging for me because these are questions that our current system has absolutely no chance of getting correct. Our current system can get about 50% of questions correct at all, like if it does the best it can do. And factoring the 60% and the 30 or 40% answerability, this is about 15 to 20% recall at 200. And there are lots of things that we could do to improve. So including bigram matching, you could also imagine that to compute our distance, we could do bidirectional Wikipedia distance. So not just answer to entity, we could go from the entity to the answer. So that gives us a better score. And we could include basic network features like degree centrality or node level metrics, and then have a classifier decide which things are important and how. And then we are also not using text-based features at all. And that's obviously something we could do, but we didn't do that because I want to know how good the network features are. I don't want to know how good the text features are because we already have a system that does that. So that's it.
So when you're taking the words from the question and you're calculating the distance from those things, so you're just going like one hop out and you're saying, of those things, could any of these be the answer? And you're like ranking them, right?
Yeah, so I'll take, for example, here, the blue terms are things that I just manually looked for these that have an exact match to a Wikipedia page. And then I say, all the things that are linked to from the Leo page, I'm going to see how far are those away from each of these things mentioned. So I'll have a set of vertexes that are formed by getting all the neighbors of Leo and invented and moving parts and refrigerator, and then I'll compute the distance of each one of those to all of these. The hope is that the answer is close to all of these.
How close all of those words are to the answer themselves, right? Like, so is like, for example, invented, is that farther away from Albert Einstein than theory? And I'm only asking this because it would be interesting if words that occurred earlier in the question were farther away from your answer than words that occurred near the end of the question.
Yeah, I would expect that they are farther away because the clues are intentionally designed that they're not as obvious, but don't know for sure.
As the sentences keep on increasing, those are sometimes independent of each other. So does that affect the network that you have created?
I don't think so because your information is increasing monotonically, and that's the part that at least I care about the most. But I'm not sure that gets at your question.
Last question.
How did you retrieve your data from Wikipedia?
So someone very usefully created a data set of vertexes in the pages and an adjacency list. So I didn't have to parse Wikipedia in order to figure out what this graph was, which is part of the reason that I don't have the text features. But that's fine.
So you mean it's available online?
It is available online. Unfortunately, I looked and the page that I got this from is actually no longer up. But if you need the data set, I can give it to you.